Well, good morning. Good morning and welcome to Medical Grand Rounds. Giving a heads up for next week, on May 2nd, we have Dr. Carl Lorenz and Stephanie Harmon who will be talking to us on looking back and moving forward, a prospective on palliative care. Just as an extra note, because there's a conference in this room at 9 a.m. next week, we're going to end a little early, about 10-15 minutes early, Grand Rounds next week, so just as a heads up. Well, today it's a real pleasure to introduce one of our real superstar junior faculty members, Jonathan Chen. Jonathan is a graduate of UCLA, where he received his Bachelor of Science in Cybernetics with specialization in computer studies. He then went on to UC Irvine in the MSTP, where he received his PhD in computer science in the School of Information and Computer Science and his MD from University of California, Irvine. We were then fortunate, following that, to recruit Jonathan to Stanford, where he served as an intern and a resident in the Department of Medicine, Internal Medicine Training Program. He spent then 2 years at the Palo Alto VA doing a fellowship in medical informatics, and then again we were fortunate to convince Jonathan to keep his talents here at Stanford, where he joined the faculty first as an instructor and then this past year as an assistant professor. Jonathan lives in 2 divisions within the Department of Medicine. He is a hospital medicine specialist on the clinical side, and his research focus is in the Center for Biomedical Informatics Research. Jonathan's research focus is on mining clinical data sources to inform medical decision-making. I think you'll hear much of that today. And a real shout-out to Jonathan, along with Abraham Verghese, for the leadership of a standing-room-only symposium in this room last week on human intelligence with artificial intelligence. So join me in welcoming Jonathan Chen.
Thanks so much, Bob. Good morning, everyone, and thank you so much for having me here today. We'll be doing a little bit of a review of artificial intelligence and machine learning in healthcare. A little bit of the why, the what, and the how. So let's start with the why. What are we also interested in? Well, let me tell you why. It's because there's a collective anticipation for the growing potential of modern so-called AI technologies that can systematically answer questions previously thought to possibly be impossible, for a computer anyway. Questions like, is that a chihuahua? Or, wait a minute, is that a blueberry muffin? Is that a kitten or a caramel ice cream? Dog or bagel, or my personal favorite, parrot or guacamole? Technology today can systematically label every cat video on the internet and fill your Facebook feed with a perfect clickbait that will keep you distracted for hours, all while siphoning off all of your personal information without you even realizing it. Though it does get you to think perhaps there might be more meaningful applications of this technology. How about, say, hey, is that a benign mole, or is that malignant melanoma? Is that cancer? Is that normal, healthy lung, or is that an infected pneumonia? More and more, you're just going to see more examples like these where automated systems have superhuman capability to automatically answer clinical questions. And yet, medicine, healthcare, systematically lags behind other industries by a decade in terms of effective use of information technology and our real-world data. Even though, shouldn't medicine, the one place where literally lives hang in the balance, be the place where we do this the best? Consider, for example, by some estimates, medical error is the 3rd leading cause of death in America. 250,000 dead every year. Now, some argue, this estimate is just totally wrong. It's actually 400,000, because this is only inpatient coded deaths. Others say, oh, look, let's not exaggerate, all right? It's more like 100,000. Well, even order 100,000, that is still a jumbo jet airliner full of patients being pushed over a cliff to their deaths every single day. And more so, what's concerning is precisely that we're not even sure what this number is. Apparently, that is how much we care about reliably capturing and using our data in healthcare. Maybe lives are too abstract. Well, fine then. Consider the money. 1 in every $6 of our entire economy is spent just on healthcare. You see Amazon and Berkshire Hathaway, JP Morgan Chase, they're going to band together. They're going to get in healthcare. Why are they doing that? Is it because Jeff Bezos is such a nice guy? He wants to heal the sick and make the world a better place? I don't think that's why. It's as Warren Buffett says, It's because the ballooning costs of healthcare are like a hungry tapeworm slowly gobbling up the economy. It cripples your ability to do anything else. It's even more frustrating when you consider that up to a third of the $3 trillion we spend on healthcare every year is essentially waste. It's services, processes, administration, it's prices that don't actually help any patients. Perhaps it is no wonder then that many have an appetite for, are there advancing technologies, are there intelligent systems that could help us make better use of our scarce healthcare resources to do more good for more people? So that's some of the why. Most of my talk is going to be about demystifying the what. What are we talking about? Is it AI, ML, deep learning, big data, precision health, cognitive computing? No, nobody likes cognitive computing anymore. Clearly, at this point, what AI is it is a marketing buzzword. That is what it is. It is what people call AI is nothing like what I would have conceived when I did my PhD in computer science 10 years ago. I thought we would be talking about general AI systems. I thought we'd be talking about HAL 9000, Skynet, David from Prometheus, general-purpose thinking machines that can reason through complex problems, adapt to new situations, and fluidly interact with human beings. We are nowhere close to such technology. Well, then what are we talking about then? If you use a much looser definition where AI, well, that's just any time a computer can kind of mimic intelligent human behavior. Well, I mean, a rules-based expert system from the 1980s can do that. I got a rule here. A patient has fever and they have low blood pressure. I predict sepsis infection. Well, have a computer execute that rule. That's a simple form of AI, right? But that's usually not what people are talking about. Usually, almost always when somebody is selling you AI now, what they're selling you is machine learning. It's a set of tools and algorithms of which deep learning is a particular subset of those techniques. It's largely just rebranded neural networks, been around since the 1970s, but have recently been found to be particularly effective at certain tasks like image recognition. The real common distinguishing feature of machine learning is that as opposed to the classical approach of programming rules into a computer from the top down, instead, these are algorithms that learn by example. They learn by data. Here I've got 100 patients with sepsis here, and I got 100 patients here who don't. Is it fever? Is it white blood count? Is it lactate? Is it procalcitonin? I don't know. Machine, you just look at all these examples, and you figure it out. You tell me what the rules are, what the patterns are that makes that distinction. If you break down machine learning even further, actually many different subcategories of the types of algorithms and type of applications that they can be used for. But again, usually what somebody's selling you is almost always it's a supervised learning classifier. These are not general thinking machines. These are models designed to answer very narrow multiple choice questions. Here's a picture. So is that a picture of a cat or is it a picture of a tumor? I have a patient here. Are they going to die within 30 days or not? So I want to think through an example of how you might use some technology, which are very often framed as helping you predict or diagnose something. Very key distinctions. They don't tell you what to do. They just tell you what's likely to happen. Just a medical concept to think through. How do you allocate a scarce resource? A recurring theme I want you to think about where you might try to apply such things. A scarce resource like, say, organ transplants. You have a patient from chronic alcoholism, untreated hepatitis C, or maybe they got a tumor growing in their liver is shutting down, they are going to die unless they get a transplant. But if you live in an area around Stanford, our donor to transplant ratio is very bad. We don't have enough people driving motorcycles or getting gunshot wounds to the head to fill our donor pool. So eventually when a donor organ shows up, you've got 10 people who want that organ. You've got 10 people who need that organ. How would you decide who to give that organ to? This is not a rhetorical question, right? This is a real medical question that has to be figured out all the time. So there's many ways you can think through it. One common concept I've seen people think is, oh, well, just have a waiting list, right? First come, first serve. That's fair, right? Actually, in medicine, there's almost nothing we do that is a first come, first serve queue. We almost always have a priority queue. We triage people who are sicker up to the list, right? Because, look, I know you've been on the waiting list for like a year. You're really not that sick. You could probably survive another year. This guy, he just showed up, but he's going to die next week unless we transplant right now. We got to get to him first, okay? So that's actually usually how we do things. We need to get to the sicker people first is often a lament. Well, who's sicker? How do you decide who's the sickest and needs this the most? Well, it's probably the person who's in the hospital, right? The person who's in the intensive care unit. Well, you can imagine how easy it is to game that system. Well, I'm just going to move my patient to the ICU, and then they'll look sicker, and they'll go up on the list. So one other approach you might consider is a slightly more objective or consistent approach is how about if you use some kind of consistent prediction data-driven score. I don't know if Ray Kim is in the audience, but head of our GI division developed the MELD score, for example. So what is the MELD score? You use some standard laboratory results, and what it does, it's telling you who to transplant first, and how does it do that? It's separate from what it's actually doing. What it's actually designed to do is predict how likely a liver patient is to die. And so in that sense, simple data-driven models to make predictions in medicine, they've been around for decades. There's actually nothing that new about them. It's just different approaches to do it. You go to MD Calc's website, there are hundreds of these kinds of calculators implemented online now. For example, in medicine, make the distinction between what we try to predict and what we are supposed to do about it. These algorithms predict what's likely to happen if usual care happens. But in medicine, we're not just interested in predicting what's going to happen to our patient. The whole point is we want to change what's going to happen to our patients, right? We want to intervene. We want to change what the likely outcome is. So, for example, CHADS2 predicts, are you going to have a stroke? So I can decide whether or not to give you blood thinners. ASCVD, are you likely to have a heart attack? So I can decide whether or not to put you on a cholesterol medication. If you look outside of medicine, these types of models and algorithms are pervasive in our everyday life, even if you don't realize they're operating. I mean, what is your FICO credit score but a prediction about whether or not you're going to default on your loans based on how well you and other similar people have paid them in the past? What's become increasingly more popular now are automated scores. I mean, compared to this calculator, that's pretty good, but look, I got to open up another web page, I got to data entry these numbers in, and I got to pull them up one patient at a time. Now that we have an electronic medical record infrastructure, as clunky as it is, at least it exists, more and more people are saying, why manually enter in 5 variables into a web page? Can't you just use 100 variables, everything we have a record of, and automatically monitor and scan these things 24 hours a day to generate these types of predictions? So I mean, like, everybody's got some kind of sepsis early warning system right now and trying to see if they can do something to improve outcomes there. Places like the VA, they have dashboards, automatically track everybody in your primary care population and see who's at high risk to be in a hospital or die in the next year so you can deploy specialized resources. So these seem pretty cool, but how would you build something like this? How does this work? If you want to do it, the first thing you need is the data. And this is especially difficult because healthcare data is notoriously difficult to work with. It's notoriously messy. And why is that? Because it wasn't created for the purposes of things like, I don't know, learning and improving care. It was created for the purposes of billing. It was created so that clinicians can basically chat with each other, right? We can write a note about a patient in this prose form, in paragraph form. That's very nice for our expressiveness of the patient story, very hard for a computer to digest and understand. So what you'll find in a typical data science project, classically, most of your time is spent on the data janitorship, as some would say. 80% of your time is spent just preparing the data. The remaining 20% of your time, you get to complain about how you have to prepare the data. If you're willing to do that and go through that slog, usually you're hoping you're going to generate something like this. This is made-up data, but an example of a simple two-dimensional data frame, or I might call this a feature matrix. Every row represents some patient, some case you want to make a prediction for. Each column is just some descriptor, some feature about that person, your age, your gender, prior comorbidities, last vital signs, and lab results, for example. For typical supervised learning, there'll usually be one target outcome column, like in orange over here. In this case, it's did this patient die within 1 year. The idea being, when a new patient shows up, you can measure all that stuff, all the descriptors about them, and then you want to make a guess, a prediction. Well, what is that outcome going to be for this person? I don't know yet, using information based on all these patients we've seen before. Visual example to make this a little bit more concrete. Let's simplify this. What if we measure just 2 things about our patients, heart rate and oxygen, that we can plot them in this 2-dimensional space? Patients come in the emergency department, short of breath, CT scan them. Oh, they've got a pulmonary embolism. Ooh, looks bad. They need treatment. Maybe they should come into the hospital. So the ED calls me, PE, you need to admit this patient. I'm like, whoa. I mean, look, I'll examine the patient. Let me check him out. But can't you just, like, put them on blood thinners and send them home? I'm pretty sure they're going to be fine. But something bad might happen. You better admit for monitoring. Okay, I'm going to examine them. I'm going to look at them. Look at these hands. I'm going to lay these healers' hands on them, and trust me, I know they're going to be fine. You can trust me, I'm a doctor. And as much as I joke about that, expert intuition is actually extremely powerful and extremely potent. The challenge with it is it's very hard to reproduce, which means that it's nearly impossible to deliver consistently and at scale without some kind of support system. So here's another way you might go about it. So these are a bunch of PE patients. We measure their heart rate and oxygen. Blue represents patients who, they did fine. You gave them treatment. They went home. Nothing bad happened. Red are the patients who something bad happened. They ended up needing to be intubated in the ICU, or they just died. So what would you do then, say, if Mr. Green showed up in your emergency department? You did the scan. They've got a PE. They're here on this course. Should you send them home? I think they're going to be OK. That's what my intuition tells me. But how about we use our prior data? How can we use that to help inform this decision? Well, what you could do is you could draw a decision boundary, a line through this data in a mathematically optimal way that pushes as many blue people to this side and as many red to that side. And if you do that, you could say, you know what, it sure looks like Mr. Green is more like a blue patient than a red patient. So now in a quantitative way, I feel even more confident in what I was already intuiting, that this patient's going to be fine. Just give them blood thinners, send them home. I think they'll be OK. But what would you do if you had different kinds of data, right? All those things I've showed before, classical research tools, logistic regression, Cox survival models, basically do that. They draw lines through data, and they can already be quite effective. What if your data looked like this? The red patients and the blue patients, they're clearly different, but there's no way you can just draw one line through that data that makes sense, because there's some kind of nonlinear interaction. You know, right? Your shock index. Is it your heart rate that matters or your blood pressure that matters? Maybe it's the ratio that matters. Is it your rapid shallow breathing index? Is it your respiration rate or is it your tidal volume that matters? It's actually maybe the ratio that matters. And a ratio is a nonlinear interaction. You can't draw a line through that kind of data unless you specifically look for it. So looking at how maybe different machine learning algorithms have much more flexibility to adapt to situations like that. Here are 3 example input data sources, red patients and blue patients. And here's an example of a couple algorithms trying to figure out how to separate the world into red and blue spaces. If you're working with a purely linear method, you can only draw a line through the data. And even though look in the middle, that's clearly 2 concentric circles of blue and red, right? There's no way to draw a line through that. If you had a much more flexible method, in this case, a nearest neighbors method, you can get much more flexibility to model what's happening there. However, it's also worth pointing out, flexibility isn't always a good thing. There's something called the bias variance trade-off, where you can try too hard to match your data. I mean, look at this should just be 2 circles right down in the middle here, but you get this really jagged decision boundary because the algorithm is trying too hard to overfit the data it's seeing. But that's not really right, because we're not trying to recapitulate historical data trends. We want to make robust predictions about the future. So just be aware that greater flexibility isn't always a good thing. Here's just a broader view of many more algorithms and how they would approach these data separation problems. And worth noting, these are all standard machine learning algorithms now. Been around and proven for decades. Open source software. Any one of you can download and start using these tools right now. You don't need a PhD in computer science anymore to start doing this work. Combine that with the increasing ubiquity of electronic health data, and now it becomes increasingly possible to develop and deploy machine learning applications in healthcare. What are some other differences between machine learning and your classical observational research that you're used to? Usually when you're building a model, when Ray Kim built the MELD score, it's expert knowledge. I think creatinine matters, that's your kidney function. I think INR matters because it's about your hypercoagulability factors, right? And let's pick about 5 of those, not get too crazy. Machine learning approach is like, I don't know what matters. We have all this data, just pour it all in. Pour it all into this pile of linear algebra and let's see what comes out the other side. Let the algorithm figure out which parts of the data seem to matter. And if the answers seem wrong, well, just keep stirring and then maybe it'll start looking right. And you have ways to cope with a lot of the missingness and messiness of the data that's often prolific in healthcare data. This really points to another concept. I really want you to make a distinction. You're used to seeing observational research, basically. That's a very typical medical publication. And how does that contrast and is similar to a machine learning approach? Usually, the classical observational research you're used to is really about inference. It's about trying to explain something about how the world works. As an example, anybody here think that smoking is bad for you? Anybody think that smoking causes lung cancer? Nobody believes that smoking causes lung cancer? Okay, why do you believe that? Why do you believe smoking causes lung cancer? I thought we practiced evidence-based medicine. I demand to see the randomized control trial that proves that smoking causes lung cancer. It doesn't exist. For one thing, it would be very impractical to randomize people to smoking. And more so, it would be unethical to do so because the observational evidence is so overwhelming that that is the case. How does that work? Well, you just go look at a cohort of patients, right? Here's a bunch of patients, some of whom smoke. Here's a bunch of patients who don't smoke. And let's just follow them over time, see who develops lung cancer. And then you adjust for as many confounding factors as you can think of with your expert knowledge. And even after doing that, it remains that smoking is an independently associated risk factor for lung cancer. And thus, we have pretty good evidence that that is what causes it. And the reason why a lot of clinical publications like this, because just by reading that, just by learning that, that is shareable knowledge that it can be practice changing right now. Oh, smoking causes lung cancer? I should tell all my patients to stop smoking right now. I'm going to do that right now, if I wasn't already. Compare that to a machine learning approach. Usually these algorithms, they don't know and they often don't care how or why anything works. All they're trying to do is maximize prediction accuracy. So try to get the most accurate model as possible, and very often you'll end up with a piece of black box software. Hey, look, I read a publication. Somebody made a piece of software where you take a picture and it'll tell you if your rash is cancer or not. Wow, that's amazing. I'm going to see 10 patients in clinic tomorrow. They're going to complain about a rash, and having read that paper does nothing for me. I can't actually use anything after reading that to actually help my patients, right? It may be one day we'll have the IT infrastructure where it becomes possible to exchange and swap these software modules so people can actually use them. But at this point, someone writes about this highly accurate black box software. It's like, that's cool, but almost nothing you can do with that after you've learned about it. The real other key distinction I want you to think through is because these algorithms, all they care about is accuracy, because that's all you told them to care about, they can possibly make very strange associations, and be careful what inferences you try to make on them. For example, you give a bunch of clinical data to a model. I'm trying to predict patient mortality, and you will find, accurately so, patients with palliative care consults are highly likely to die. This is absolutely true. Palliative care consults are highly predictive of patient death. You all know, to put that into context, please do not conclude that firing palliative care will reduce mortality. That is clearly not what you draw from this, because you get the clinical context. That doesn't make sense. It's the confounding by indication. The kind of people who get those consults were the kind of people who were probably going to die. The algorithm doesn't know. The algorithm doesn't care. You told it to make an accurate prediction of death. It's going to use any piece of information and get its hands on to make an accurate prediction. All right, other approaches that machine learning can do. A lot of what you hear less about, what I'm often interested in, is unsupervised learning. How can you take advantage of unlabeled data sources? How do you automatically organize complex data sources? Considering that there's an unreasonable effectiveness to data. Don't get too caught up in fancy methods or algorithms people are trying to sell you. Those are important, but what's often far more important is you need the right data source to learn from. That's actually really one of the key ingredients you need. This is actually very challenging in medicine because it's so hard to get good labeled training data, right? If you want to make some accurate predictions about what this picture is, well, you need a specialist doctor probably to scan through thousands of pictures and say, yes, this is a cat, no, this is a tumor, this is something else. I want to find all the diabetics with complications in our population. Well, someone's got to manually review 10,000 charts and say, yep, this one has complications checked. Oh, this one doesn't, this one does not. Very expensive, very difficult to attain that. And we can dream about having large, well-curated, annotated data sets, which probably won't exist without some kind of robust crowdsourcing solution. Or what I'm very interested in is, what can you instead do, clever approaches to take advantage of the masses of unlabeled data that you already have available. Approaches like this is how, say, market basket statistics work. You go to a supermarket, you get a club card, free discounts on your groceries if you do that. Why are they doing that? Those discounts are not free. What they're doing is they're using that to keep track of what you buy now and over time so that they can anticipate what kind of things you're going to purchase. This is a classic, colorful story about how Target started sending targeted advertisements to a teenage girl showing a bunch of baby products. Because just based on the mundane purchases she was making, they could figure it out, the algorithm figured out that she was pregnant before her own father had. Amazon recommends to you, hey, you bought this book, maybe you'll like this one too, based on what other people have done before. Does Amazon understand what's in that book? Like, what the themes of it are. It has no idea. It just knows that this is what tends to happen together. But that already, if used in a certain way, can be a very powerful and useful method. So one of my main themes of work is trying to apply this to medical decision making. Here is a user interface screenshot from a prototype I built, how you might imagine clinical order entry working. So imagine this is Epic or Cerner. I'm taking care of my patients. I need to get their meds and labs in. And knowing nothing but their age and gender, here's just a list of just the overall, just most common labs and meds in the hospital. Let's say I want to get more specific. I'm going to search by name. This is just usual functionality you'd expect from any CPOE. Spiro, I'm looking for spironolactone. Here we go. I just ordered spironolactone for my patient. Aldosterone antagonist, good for patients who have heart failure or liver failure. And now, given that I've ordered spironolactone, the system can estimate, here are all of the other labs and medications that are very likely to occur next. And on the right are all of the medications labs that are very disproportionately likely to occur within the next 24 hours. So I can go to that list and say, hey, actually, furosemide, I did want that. That's a good diuretic. It combos well with spironolactone. Added that to my shopping cart. And now, given two pieces of information, the system kind of juggled and adapted the list here. Look on the right. What's up now? Carvedilol, digoxin, isosorbide dinitrate. It's basically heart failure medications. Below that, rifaximin and propranolol. It's basically medications for complications of liver disease. And you know what? My patient actually does have some encephalopathy. I will take the rifaximin. Thank you. Add to shopping cart. What comes to the top of the list? It juggles again. Lactulose, zinc, propranolol. Liver failure medications are starting to float to the top, while the heart failure stuff is getting pushed down because they seem less relevant. So a few things I want to point out. You'll notice at no time did I stop to data entry in the words liver failure or ascites, let alone look for the ICD-10 diagnosis code in a drop list. I'm just taking care of my patient. I'm just putting in the medication orders, the things that I was going to do anyway. But if the system can pay attention to what I'm doing, it should be able to infer a lot of the clinical context and anticipate what I want without me even having to ask for it. So how did I do this? Did I laboriously do a manual review of all the clinical practice guidelines and figure out what the medications and lab tests were and encode them into the computer? Did I hire 100 doctors to review 10,000 patient charts and ask them, can you annotate all these charts with what you think the right treatment was? Well, no, because I can't afford to do that, right? But in some sense, maybe I don't have to do that. Because what do we do in clinical practice every day? We are essentially an army of manual annotators. Every time we take care of a patient, that's what we're doing. I'm learning about my patient, I'm understanding them, I'm going to spend the time to synthesize that information, and I'm going to give you my best guess of the appropriate treatment and diagnostic plan manifested in my clinical orders. That is the concrete manifestation of my clinical decision making. And so thus, very broadly, one of the core themes of my research is how do we take advantage, how do we discover and distribute that latent knowledge embodied in our everyday clinical practices and make that into an executable and reproducible form? So what do you think? Does this seem good? Does this seem cool? You like it? You like it? Anybody worried about ways that this could go wrong? No? Okay. All right. Well, I've got a couple ideas about ways this can go wrong. Some people lament, wait a minute. You start recommending stuff. Isn't that just going to lead to overutilization? Amazon recommends you a book. They just want you to buy more stuff. That's not what we're trying to do in medicine. Actually, probably completely true. I think that's a very possible side effect. You will get more good decisions, but you might get extra wasteful decisions as well. You could, another line of work that I'm developing right now is just apply it to the inverse use case. Hey, before you order that back MRI, before you order that thrombophilia workup, did you know it's highly predictable that's only going to be abnormal 2% of the time? And only 1% of the time does it actually lead to a change in management. I'm not telling you that that's the right or wrong thing to do, but maybe you should reconsider that before you go down this pathway. It really gets to a much tougher issue, which is fundamentally, do you believe in the wisdom of the crowd? Or do you fear the tyranny of the mob? I'm actually not sure about that some days, but in any case, it's actually really hard because just because something is common doesn't mean it's good. Really hard to unpack in medicine because there is no gold standard to define what good medical decision-making is. Look through all my research and papers if you want to see more of the details, but here's at least an anecdotal example to help you think through the concept, the strange concept of why this even might work. You guys remember? Who Wants to Be a Millionaire? TV game show. Answer multiple choice questions for big money. The classic thing about this game show is if you're stuck, you've got lifelines, classic lifelines. Phone a friend. What is that? You get on the phone, you call anybody in the world you want. Who are you going to call? I'm going to call the smartest, most knowledgeable expert I know. I'm going to consult a specialist who can give me the right answer, right? Another approach, you can just ask the audience. We'll just take a poll of the studio audience. It's not knowledgeable experts, it's people watching a TV game show. So how well do you think these two approaches work? It turns out that if you phone a friend, they're right about 2/3 of the time. If you ask the audience, they're right like 91% of the time. What on earth is going on? And to be clear, this does not mean the audience is filled with geniuses and 91% knew the right answer that you didn't. No. In this case, only 55% of the people picked the right answer. It's just that this majority vote turns out to be right 91% of the time, as strange as that may seem. There's actually mathematical theorems for why this surprisingly works. It's why you trust a jury of 12 commoners. Shouldn't one expert judge be smarter? Maybe, but as long as the individual component voters are better than random at guessing the right answer, aggregating many can be very helpful. It amplifies that signal. This example also does point to another issue, though. In the Russian version of this game show, they had to turn Ask the Audience off. Because I guess Russians don't like watching other people win money or something. So they would deliberately feed contestants wrong answers, rigging the voting system to sabotage them. So just beware. This should work well as long as the audience, the crowd you're learning from, has goals that are well aligned with your own. And if they don't, you're in trouble. So as excited as I am about the potential of these types of so-called AI technologies to enhance and improve medicine, I've also been getting worried the past few years. I wrote this perspective in the New England Journal last year. What this is, I reference this, the Gartner hype cycle for emerging technology. The x-axis is time, and the y-axis is hype. It's expectations. It's how excited people are over new technologies. The reason I'm getting worried is notice what is at the very tip top of the peak of inflated expectations. It's machine learning, deep learning, it's AI technology, right? I'm worried because I know exactly what's going to happen next. We are going to crash into the trough of disillusionment. You can see blockchain is already on the way down. People are going to be mad. They're going to be resentful. It's like, whoa, I had all these promises and expectations. What happened? I thought 80% of doctors were going to be replaced by algorithms. I thought pathologists, radiologists, you're all fired. I thought if we just poured all this data into the computer, that out would come the cure for cancer. Why is this not happening? I'm not really sure those were the right expectations to have. Even though there have been amazing achievements in artificial intelligence research in the past few years. Go, classic ancient game. I had a classmate in PhD who was working on algorithms to play this game, and he lamented, this is probably impossible. This game is just way too complex. It's way, way, way harder than playing chess. It's far more complex, all the branches you have to think about. About 2 years ago, DeepMind, a company in the UK, they've since been bought out by Google, developed an algorithm that can beat professional Go players. It was an amazing achievement in AI research. A similar algorithm they applied to playing Atari games. They didn't program the computer to understand Atari games. They just fed the pixels off the screen into the algorithm and the score that the game was getting. And this algorithm just started playing around and eventually was able to figure out on its own how to play these games. Just last year, Carnegie Mellon put out a poker bot beating professional level players and no-limit Texas Hold'em. If I wasn't in medicine, I would love to work on this stuff. It's so cool. As a tech nerd, I love this stuff. But come on, we solved Go. We've got self-driving cars. How come we haven't solved medicine yet? Come on, get to it already. I adapted this slide from Marty Tenenbaum because it had several excellent points. Why is there a difference? Well, you got Go, you got self-driving cars. Those are static games. It's the same rules. You know them. You've known them for hundreds of years, if not thousands of years. Medicine evolves to new technology, epidemiology, social factors. There's no ground truth to converge upon. We're never going to be done studying medicine. It's a moving target we have to keep chasing. The key distinction is that when you have a video game, you have Go, simulation and experiments are trivial and they're easy. You can have a computer play 1,000 games of Go against itself, really simply. Can you simulate medical care for a patient and know what the outcomes are going to be? That actually might be impossible. I don't really foresee that happening anytime in the near future. Which means, how do you get data? How do you get information? How do you run experiments to learn? A video game, whatever. Just have a computer run a simulation, run the experiment. Easy. If you want to experiment on people in medicine, that's extremely expensive, and when you get it wrong, you kill people in very bad ways. If you want feedback, did you pick the right chemotherapy plan? You could be waiting 5 years before you know the result. That time cycle is way too slow for a lot of these reinforcement learning approaches in automated systems. I'll disagree with the last point about data not being existent. I think actually a lot of the data we want does exist, but it's very hard to access, right? It's locked up in healthcare system silos who have no incentive to want to share with anybody. They only see risk. They don't see the upside to it. And the reality is I don't blame them because of how their incentive structure is organized. And then even if you could get access to the data, notoriously messy, hard to use because it was not created for the purposes of these types of applications. If you did want to go about doing something like this, how do you start? Well, one thing, collaborate with somebody who is looking to collaborate with you. Know that at the end of the day, nobody wants technology. I got AI this, I got AI that. You know what? Who cares? Can you solve a problem for me or not? Can you solve a medical or business problem for me or not? Which is why you really need the tech people to combine with the clinical experts, the domain expertise to understand what the right questions are to even ask and how to use that information. Think about a case where an important decision hinges upon a human making a prediction about the future. I predict this patient's going to be fine if you set them home. I'm pretty sure. I predict this patient won't get readmitted within a week. I'm pretty sure. We have very good intuition, but very variable once you start having dependence on individual humans making those calls. Support them with data-driven algorithms can at least make that more consistent. Remember to make the distinction between these systems make predictions about what's likely to happen. They do not tell you what to do about it. You've got to separate the prediction from the action and know the context about what action you actually have available to do. Don't get enamored with any specific algorithm. What's far more important is that you have a good data source to work from. Like, here's an idea. I'm going to prescribe 100 Vicodin to my patient. I'm kind of worried they're going to like divert that and sell that on the street. Couldn't you like predict whether that's going to happen? That would be pretty neat, but how would you ever know if you were right about your predictions? How would you ever get a signal, a target to aim for? Maybe instead, this patient's about to get a surgery. Can you predict whether they're going to end up needing multiple opioid prescriptions within next year? You could try to predict that. You have the signal for that. This is relatively crisp data. Again, back to the point of actionability. Very often I see like early warning systems. This patient has fever, low blood pressure, and you ordered a blood culture. I predict they're going to have sepsis. Like, okay, well, thank you for that prediction, because I didn't already know that. Why do you think I ordered the blood cultures? Think about, what is someone supposed to do about it? What am I supposed to do about that prediction? Often these come with, I recommend you pay more attention to your patient. Well, thank you for that recommendation, because I wasn't doing that already. What may be much more effective, think in terms instead of a scarce resource you have that you know works well, is highly effective, but you can't deploy it to everyone. So for example, the VA, they have these intensive primary care teams, a specialized social worker, a pharmacist, a case manager, an extra doctor, and they want to help their especially sick patients to keep them healthy and out of the hospital. You can't deploy that team to everybody, nor is there any need to. Most patients are going to be just fine if you just leave them alone and do nothing. But can you predict for me who are the 5% of patients who are going to consume 50% of our healthcare resources next year? Then I've got a target to deploy my scarce resources. Targeted advertising, basically. This is actually a really controversial point about whether or not it is essential for algorithms to explain themselves. I'm going to go with, I actually don't think it's explanations you want. What you want is confidence. What you want is trust. Can anyone explain to me how propofol works? Anyone explain to me how Tylenol works? I don't think nobody can, because we don't understand the mechanism of action of many of these drugs, but I'm still willing to use it. So apparently explanation is not essential for us to use something in medicine. The distinction is, in medicine, I use Tylenol because I know these drugs have gone through safety trials, they've gone through efficacy trials. Most of these algorithms have not been held up to that level of evaluation. And that's why we want at least explanation as a crutch to make us feel better about what's happening, even though that's not really what we're looking for. We're looking for confidence. We're looking for trust. Bear in mind that incentives are everything. There's so many good ideas that everyone in this room can come up with that would make medicine better, but most of them, there's no sustainable business plan. You can't actually get them to work or keep alive, right? A lot of the ideas you might come with depend on value-based payments, and we're still 90% in a fee-for-service world where we get paid more just to do more. So that example, like the VA can do this. Hey, I'm going to watch all your patients in the primary care population. If they're really sick, I'm going to keep them healthy, deploy these special resources, keep them out of the hospital, right? That'll be great. You go to your hospital executive, say, I'd like to download all your data and help me build the system. Wait, you just found a way to turn away all my paying customers? I'm not really sure why I want to work with you. There's all sorts of distortions in the way we're set up to want to do good. Consider also, think of different applications. As doctors, we naturally want to think of clinical applications. What does a doctor think of and what could they be doing better? Very fun to do. A lot of risk, though, if you do that wrong. Think of operational, administrative applications. Much lower hanging fruit, probably much more ripe to actually make some progress and deliver value much sooner. Can you predict how long this patient's going to be in the OR so I can make better use of the OR time, a very expensive, scarce resource? Can you predict which of my patients are not going to show up in clinic so, again, I can make better use of that schedule? Can you automatically fill out all my prior auth forms so that they'll get approved the first time so I don't have to deal with that? Can you automatically transcribe my patient encounters so that I don't have to spend my time just transcribing notes? Probably much more tractable things, and you'll get into less liability issues if you get this off the ground first. All right, I'm going to wrap here. Coming back to that hype cycle, I'm worried about that crash. I hope with the kinds of discussions we're having today, we can foster a better appreciation for both the capabilities and the limitations of such advancing technologies, so we can soften that crash into the trough of disillusionment and quickly move on to the slope of enlightenment, where we effectively use every information data source to improve our collective health. So what do you think? Are computers going to be smarter than humans? Maybe the other way around? That makes for a very stimulating debate. I find it's largely irrelevant. It's the wrong question to ask. Because the answer is, combine good machine learning software with the best human clinician hardware, and together we can deliver care that's better than what either could do alone. Thank you. We'll take any comments or questions.
Jonathan, that was really terrific, and I want to use your visual. I want to use your visual of the trough of illusionment.
Yes.
IBM Watson may be in the trough right now. And so what happened? What went wrong with the Watson experiment at MD Anderson, and was that predictable?
So for those not familiar, IBM Watson, which I'm very excited about, I think I have a slide in here about them crushing Ken Jennings at Jeopardy. Oh my God, it's amazing. But notice that it only tends to answer what questions. It doesn't answer why or how. And I think that was mostly a marketing hype problem. They've been very good about their marketers have been very driven about doctors or computers going to do all these amazing things. I think they're actually doing some excellent work and there's very good research there, but clearly their marketing department just got out of control and really overpromised what's possible. The MD Anderson one, that flame out, I think it was like $60 million or something like this. That sounds like more of a business issue more than really an application issue. They kind of bought in, poured the money in, just assumed something would come afterwards, but didn't think through. The algorithm is pretty cool. That's actually a really, really small part of a solution, right? You have to do an end-to-end closed learning healthcare system loop and figure out how you're going to deploy that in workflows and answer questions that doctors or nurses would say, I didn't ask that question. I already knew that answer. That doesn't help me, is some of the things that they should have thought through. But I actually think they're doing very good stuff. It just clearly got overhyped.
Perhaps I can ask a question. I'm a big fan of Alvin Feinstein's book, Clinical Judgment. And when he wrote that book, he thought that clinical judgment, his focus was on making us as clinicians better collectors of data from the patient. Not focusing on paraclinical data of the sodium and the CBC, but making us consistent in recognizing, say, signs of sepsis and so on.
Yes.
Where do you see some of this work? How can we move into that space? Bring us back from evidence-based medicine that's so focused on abstract data, so removed from the patient. How do we bring some of this to bear on making us better collectors of data from the patient as human beings?
Better collectors of data as human beings. Extremely important. I think it's actually hard to conceive of computers taking over that anytime soon, because that's actually what we are just way better at. Given structured data, the sodium value, that's very easy for a computer to compute on. But patient looks a little clammy, they look a little mottled, they look a little under duress. A computer doesn't really perceive that very well. And even though a lot of algorithms, diagnostic algorithms, want to use that information, but they completely depend on a human abstracting that out. So I actually don't think computers are going to be able to get into that space much sooner, and why it's so important to have that partnership between the human clinician. We use the software to help you where you can, but such an important part of why our examination, our assessment is so important.
I mean, just to add to that question, part of that assessment was the patient's story. You don't think that machine learning one day is going to be able to listen to that story and abstract the patient's individual story for clues that we might miss if it does, collectively hundreds of patient stories?
I think, well, one day is a long time. Andrew Ng has this very funny thing. He says, look at this exponential curve here. We're basically right here on this curve, and AI is going to get us there. And the funny thing is, I could have drawn that dot anywhere, and it's still true, because it's an exponential curve. Okay, math joke. Anyway, so I think a lot of that will be possible pretty soon. Well, I don't know about pretty soon. Can the computer just automatically transcribe our notes? And the real reason people like Google want to do that is they want your data, right? Remember that shopping card, the club card? They don't care about helping you right now. What they want is they want your data. They want to record all your medical conversations, and with that, see if they can abstract out little pieces of information that can make them make better predictions. And there should be some useful value in that, but at this point, I think largely unrealized.
Hey, Jonathan, great talk. Just to piggyback on Abraham's comment or question there is, in terms of the patient story, can we use machine learning or computers to collect the story in a more standardized way? Because a lot of the story and what you ask patients is based on where our experiences and our backgrounds, and depending on how you ask the story, you get a different response.
Right. To some degree, I still think that's why there's a really important art to medicine. And if you think about it, it's not really art. At some core of it, it is some kind of knowledge, right? You ask a sequence of questions, you adapt it. Oh, given that the patient said this, that leads me down a different path. You're actually applying a very robust form of intelligence in doing so, in knowing how to get a history out of patients. A lot of examples like, here, given the patient history, tell me the diagnosis. But that's not how we practice medicine. We got to figure out how to get the relevant history. So there's a lot of important aspects to get from there. Can machine learning software help? It can, but it's like the workflow. How do you integrate that into a useful way? Do you want the patient to automatically fill out a form? That would be nice, because then they can do it. Usually they don't want to do it, or they answer things in strange ways. Bayesian networks, dozens of years ago, they said, oh, well, I know the next question, the next symptom you need to tell me to help me make the next best guess for diagnosis. That kind of technology has been around for a long time, but who wants to use it? These are harder things to think about to make it worthwhile to implement. Potential, but it's all about how do you imagine it actually interfacing with humans.
Thanks for the nice talk. Now that I know what you do during the day, try to drive liver doctors out of business.
Wasn't me. Hey, I was the one who made the MEL score.
So in the recent wake of the Facebook and Cambridge Analytica debacle, we generate, I don't know how many gigabytes or terabytes of data we generate in healthcare, which could be all useful. There's a HIPAA that limits that, and I have mixed feelings about how constraining that might be. But at the same time, obviously, there's the privacy issue is real.
Yes.
So where do you think the optimal balance is that will protect our patients, but at the same time that will lead to the innovation at the next level with regard to that?
You got it. I mean, really, this question is about the balance between things like innovation and privacy. That's really complicated. I definitely don't have the answer to that. I think it's appropriate that we have a tension over that, and we don't feel good about anything we come up with, because there's just going to be trade-offs to do. It almost seems irresponsible to not use all that historical data that we have on medical cases, right? Building collective institutional knowledge, so we're not just each one individual doctor trying to make our best guess. I haven't accumulated 40 years of experience yet, but collectively we probably accumulate hundreds of years. So it's almost irresponsible to not use that to make better care for our patients. But as in this Cambridge Analytica case, you can also easily see how things could go very wrong. Different countries are actually, in some sense, a little bit more flexible. They have national healthcare records that make that more possible. I definitely don't know the right answer to this question. We had a very good discussion at our symposium last week. Rob Califf, the former FDA commissioner, I don't think he had the answer either. He said, whatever it is, clearly our current approaches to regulation are not going to hold up and aren't going to work. I don't have the answer. If anybody has any thoughts on that one, I think it's appropriate that we feel bad or have a tension about this, because that balance has to be struck.
I like your example of a machine learning algorithm that would keep people out of the hospital and then going to the hospital administrator. But of course, there's a flip side to that. You could take your machine learning algorithm and go to an insurer, and then they would embrace it. And then I thought the next step would be then the insurer would tell me that I can't admit my patient to the hospital and wouldn't give me a choice.
Yep.
That's something
already happening.
Does that something that worries you?
Obviously, it worries me. It's a question of all balances and trade-offs. But yes, in some sense, insurance companies should be the most interested in predictive technology. Because that's what they do. That's their business, is actuarial estimation. Who's likely to die, who's likely to improve, who's not, so they can know how to price you, basically. The real thing the insurance company wants to do is like, whoa, you're going to be really expensive next year? How do we cut you off our insurance rolls? That's what they would really want to do. It's kind of illegal for them to do that now. It wasn't 10 years ago. So yes, it's a worry. There's pressures from all sides. But the ballooning cost of healthcare, we've got to do something also. So again, that's one where I think there's appropriate tension. I don't want an administrator. I don't want a bean counter who's never touched a patient before in their life telling me how to do my job as a doctor. But I'm also trying to be cognizant of these bigger social factors that are complex between the individual and the population, who often actually have conflicting goals, which are hard to reconcile. So yes, I'm worried about it. Tough thing to answer. I don't know, Steve, I bet you have a comment on that one.
Sort of. So first of all, Jonathan, thank you very much for your unusual, brilliant, insightful, and at times hysterical talk.
Just a little unhinged was all I was going for.
No, you said your alternate career was as a comedian, and I can see it. I can see it. I don't think you should give up that dream. I really don't.
I said, look at Ken Jeong. He was an internal medicine physician, jumped out of a car naked on camera, and now he's a movie star. So never too late.
We can all aspire to that, I suppose. And but my question is a little out of the box, even for this talk, and that is, I was inspired by your last statement that the machines and we're on the same side, right? And Donna Bedian, who's a famous quality measurement expert, said the secret of quality is love. And I think that maybe the real promise of AI is it's going to free us to love our patients more, to be able to excel in human-human interactions. Do you think that's true? And if so, what can we do to further that goal?
I think that definitely is something to aspire to, and I think some of that will happen. It's like, as a doctor, don't make me a data entry clerk, right? That's so much of what the computer does to us right now, for some good reasons, but that's not actually very good use of our time. So these advancing technologies automate some of these administrative tasks, give me time back so I can do the things that matter, right? Get the patient story, get that information that nobody else can do unless a good history taker or examiner can do. Eric Topol brought up some similar ideas at a symposium last year, and I challenged him with this question on purpose because I knew it was going to be a tough one. Now, not like I have the answer now, was if we do that, automated technologies make the visit more efficient so we don't have to do all this data entry, right? I can focus on my patient. That's what's going to happen? Or is an administrator come in and is like, oh, you got more time? Awesome. You can see twice as many patients now. I think there's going to be existing an appropriate tension for that to happen because there's going to be a shortage of doctors, basically. Even if you want more time with this patient, that's another patient who you're not seeing at all. And there's people on 6-month waiting lists to go see a specialist. And I've had patients sitting on cancer, it turns out, because they just couldn't get an appointment that fast. So I think these technologies will help us, give us more time. I'm not so sure that the system will be giving it back to us, though, unless we say something about it.
I'm right here, right in front of him. So one thing that goes really hand in hand with your comment, and something I've picked up at, is pretty much anytime you go to the doctor these days, they sit at their computer and they're typing in what you say, and they turn to look at you, ask you a question, they type some more, turn to look at you, type some more. And yeah, exactly. And I feel like that's really impacted like the physician-patient relationship, especially when you're just coming in, it's a big system, you don't necessarily trust them, and they're looking at a computer. It really takes a lot of the humanity out of it. And I think one thing that you touched on, and you also touched on, that's in place with the current system and incentives could be this idea of using natural language processing to essentially scribe for the physician so they can look at the patient, and it could at least just give a preliminary note that the patient or the physician could edit. And I just want to ask, do you know anything about what the current state of natural language processing is in terms of machine learning and AI?
In general, natural language processing to automatically understand human language, it's at best pulls out like concepts. Yes, I see you mentioned heart attack. I don't really know what the context is, but I know you mentioned it. That's already can be start to useful, but it's certainly not to the level you probably need it to be. You can do automatic human translation from English to Farsi just because you've memorized 1,000 books before, and I don't even know what this means, but I can match the words. Many people are working in that space. I have no commercial affiliations, but for example, Augmetics, that's really cool. You wear Google Glass, you just talk to your patient, and then somebody's just transcribing that. Wow, that's an amazing algorithm. You know that algorithm is a mechanical Turk. It's like somebody in India who's basically just watching your video conversation. But many people, I think Google and Microsoft have collaborations right now trying to do this. They're recording the conversations. The real reason they want it is to get that data. So at least one good thing they could do is, can you auto-transcribe some notes, and maybe auto-make some suggestions to me. People are working on it. I'd say it's pretty early stages at this point, though.
Jonathan, I want to thank you for your leadership. Also, Sonu Tadani was very instrumental in last week's conference.
The real driving force.
Thank you for a wonderful talk today.
Thank you, Dr. Rees.